Okay. Hi everyone. Welcome to another Plan Talk. This week, Nirmit Joshi from a PhD student from TTIC is gonna tell us about the paper, a theory of learning with autoregressive chain of thought. Thanks. Go ahead.
Thanks. Thanks for inviting me. And it's been a pleasure to work on this project with a lot of incredible folks, Gal, Adam, Surbi, Joyan, Theo, and Nati. So the setup of this work is to really understand this paradigm of learning with autoregressive chain of thought. So what is the premise of this work? So the current paradigm of training LLMs is very complicated. It has like several phases like pre-training, post-training, and now also inference time compute, where they just like do a lot of different things in order to accomplish one goal, which is like given a prompt, they have to come up with good response. And there are many moving pieces here, but somehow some fundamental aspects remain the same. So there are two things. So one is like they take some model class, which is like sequence to next token predictor class, like transformer. And what they do is they train them on a lot of large scale sequence data that contains highly informative traces of chain of thought, which includes like step by step math solutions over the internet, textbook data, or sometimes even like explicitly collected data that are designed for the task, and that they contain chain of thought about the task that they care about explicitly. And the goal is that how do we kind of bring up a toy model? Like for supervised learning, we have this very classical, probably approximately correct pack style model where we can ask like bunch of interesting questions, even though the direct, so for example, we can say that we get IID data from some distribution and some ground truth, and then we want to generate new, like we want to give answers on new x's so that we kind of agree on this like new y's that will be generated from the same distribution. And we have this like very stylized model, even though direct assumption that this pack model puts forward may not be satisfied in the practice. We have this sort of good theory of asking important questions like what is the sample complexity of learning, what is computational complexity of learning, and such. And the question is that the supervised learning framework is no longer relevant, or I can say is that it doesn't capture a lot of the aspects that are kind of relevant to the current paradigm of training. And the question is, how do we come up with like sort of stylized model, which is not complicated enough? It probably removes like many aspects of this complicated pipeline, but somehow it keeps like the minimal info, like minimal changes that one needs to do from for supervised learning, and allows us to ask like a lot of interesting questions that are probably relevant to the current practice, and then we can answer them within that framework. And that was sort of the goal of this work. So it's like, yeah, can we come up with a clear abstraction to understand phenomena related to this paradigm of training? And can we capture like minimal aspects of this framework while removing like a lot of details that are still important for people who are really training them? But for theoretical point of view, can I like probably remove these details and give a clear um, answers for like some direct questions that I care about? So the plan is going to be as follows. So what we do in this work is we introduce like probably approximately correct pack style framework to model learning with and without autoregressive chain of thought supervision. And then within this framework, we ask like very basic questions from mostly from learning theoretic point of view about sample and computational complexity of learning, both with and without COT. And we try to contrast between these two approaches. And the in the final, like I need this development in order to arrive at something that the like why are we why what is the sort of like power of this paradigm of training some kind of attention based architecture with chain of thought supervision? It's mostly counterfactual, I should say, that it is kind of motivated by the success, but it's kind of a new explanation that is independent or like new from all previous explanation that I have seen about why should we what sort of power does it bring, this paradigm of taking something which is as some kind of attention mechanism, and then once you train this kind of architectures on COT data, which are highly informative traces of chain information, what kind of universality one can enjoy with this paradigm? So this will be this, but before getting to this universality result, I will need some kind of setup and sample and computational complexity basic understanding. So I will spend some of my time there. And before getting into this technical setup, even I should like just tell a bit about what one should take away from this talk or from this work, depending on what situation you might be in. So if you are generally theoretically oriented person, then the framework is here really interesting. Like it captures sort of minimal aspects of this sequence to next token predictor and chain of thought supervision. And within this framework, you can see that you can ask a lot of questions. And like and the another thing is like this idea of taking inspiration from computational processes to arrive at some kind of learning paradigm is pretty old one in learning theory. So sort of like what is sort of like one good reason that we should use like attention based architecture like transformer and continue to train on this COT traces of data set, the sequence data sets, and what is sort of this computational process theory inspirational derivation of this architectures and this paradigm. This one might be interesting to you. And if you are a learning theory community, if you are one of the learning theorists, then of course these two are important for you. And another thing is like within this framework there is a lot of things you can ask. There's a lot of mileage within this framework that you can ask question that could be directly relevant to practice. This is one thing that one you should take away. And if you're a practitioner, then unfortunately not much, at least in my talk. Hopefully, as I said, like there are a lot of interesting questions that one can ask that could be then relevant to practice. But for us here, this is like a really a setup paper. This is not like any of the theorems are not like too difficult to understand, or like they're not gonna change the way you are gonna do practice. But yeah, there are like a lot of interesting questions. If they were answered, then you can still then they might be interesting to you. So hopefully some of you people can solve these questions, and next year or some other time this could be interesting. But so far it's gonna be just like basic setup theory paper with very basic theorems and question and answering, mostly in the language of learning theory. So this is gonna be our plan. So yeah, so let's see. So we are looking at time invariant autoregressive generator. So the premise is this. So when you ask these models a question like this, they generate a sequence of tokens and then they arrive at the final answer. So what's going on here is that you have a sequence to next token generator like a transformer, and you have some input mapping, input sequence, which is a prompt, and you define this f bar operation, which is output append operations. You just generate a next token and you append it to its own input, and that becomes like a new string. And then you apply this multiple times. You apply this f bar operation multiple times, depending on whatever is your generation length, how many tokens you want to generate. And then you take its last bit, last token as the output. Okay, and this is my notation that FCOT of last token is -1, the last coordinate of this sequence, and that I'm going to call end-to-end mapping after t steps. So what I have is FCOT, which is like a sequence mapping from input, and then I have this final token as the answer. And the view I would like to enforce on you is that this X is a prompt. It is like question. And then this intermediate token, this entire sequence that it generates, it's a chain of thought. And the final token of it is the answer. And now I'm going to look at this from learning theoretic point of view, that I have some hypothesis class of this sequence to next token generators. And once I fix on a hypothesis class of sequence to next token generators, it's going to induce a class of this end-to-end mappings. And my goal at the end is to just learn this end-to-end mapping. I'm soon going to be defining this learning goal in the next slide. But one thing that I would like to emphasize here is that the important aspect here is that this process of auto regression here is time invariant. In particular, I'm taking the same function from my hypothesis class and applying it multiple times in order to arrive at the final answer. So this is my end-to-end mapping class is generated by applying the same function to the input again and again. So this is kind of a key distinction from Malak's work, which we were inspired by directly to understand autoregressive learning, who took a different function for each time step. And this distinction is going to be very crucial for me as I move on in my discussion. So any question about this setup so far? Great. So let me move on. So we are in the distribution-free realizable learning setting where the setup is simple. So you have a base class of sequence to next token generator, and there is some generation length t. And my goal is to define learning goal on this end-to-end class that my goal is to define learning goal is on this end-to-end function class. And I will have some unknown distribution d and some unknown ground truth f star from this class. And I'm going to get IID sample from some distribution. And I'm going to define two setups. One is end-to-end learnability, which I'm going to call end-to-end learnability, where I just get X and Y pairs without observing the chain of thought. And Y is my end-to-end mapping. So you can think of this as I get question and then I directly get the final answer. I kind of keep this chain of thought hidden from you. And one is COT learnability, where I also tell you like what is question, what is final answer, and also I tell you the entire chain of thought in between. And our goal is to gonna be to contrast between these two approaches. And in either cases, my goal is gonna be to just minimize the end-to-end agreement error. In the realizable case, like this is debatable objective, but in the realizable case, there is not gonna be much difference whether you agree on the entire chain of thought or you just agree on the final token. Uh, and the entire paper and in this talk, I'll just gonna talk about realizable learning settings. So for me, this is fine. Like like whether I agree on entire chain of thought or just the end-to-end error is very minor distinction for me. And the question we want to understand is like, what is the complexity of learning this end-to-end mapping in either of these two settings? In terms of abstract properties of the base class and the generation length t. What is the complexity as my generation length t scales and different properties of my base class, which is kind of my supervised learning problem of learning the next token prediction. So this is the goal. So any question about the goal? Okay, great. So just I want to comment a bit about this COT supervision that uh, so the current training paradigm is pretty complicated, but I'd argue that this COT supervision is really real. Like it's really happening when we train these models. So this happens at two levels, in my opinion. So one is during post training, first of all. What they do is like they for whatever task on which like COT data is possible to collect either by human experts who can come up with the COT data, or even these days like even the strong models are generating this rich chain of thought for the tasks. You force your model to kind of predict this COT in the next token prediction manner, and you enforce your model to kind of enhance this behavior. So this COT is also most of the time referred to as prompting technique, where you just ask model this question, which is like, oh, can you come up with a step-by-step solution, or can you think step by step? And somehow they elicit this long chain of thoughts, and then they arrive at the final answer. For me, this is going to be very small distinction whether you prompt or not. Of course, this is the reason why these models are you can elicit this behavior from these models to generate this chain of thought is because such a generation was learned in the first place. And the way it is learned is like currently in the current pipeline, it's very murky. But in my opinion, it happens at this supervised fine tuning phase or even this pre-training phase where you just kind of take the entire internet and try to learn the next token prediction over this entire like whole of text data that is existing. Even this data that we have during pre-training is more COT like arguably than the end-to-end data, where you have like a lot of textbooks where you have the step-by-step math solutions. And then of course there is like a lot of transfer learning effect that happens. But if at least even in the supervised fine-tuning phase, these companies are really investing monies and efforts to collect this type of data set. So this supervision really happens. And then there are other phases like okay, RL, which are directly based, which are kind of bypassing this barrier. But this COT supervision really happens at some point during the training. This is what I want to say. And there are also many tasks which directly look at the contrast between these approaches, like, oh, what if I train my transformer on just like the final supervised data, final this end-to-end data, and what if I provide this internal chain of thought in between? So I'm just referring to this Suzuki et al. Paper where they just look at this parity task, which will be probably presented or it has already been presented in this seminar, where they look at this parity task and they ask, okay, what if I just train my parity task without observing the chain of thought? And what if I do this by observing a chain of thought? And they try to get separations. And this really happens like and a lot of this papers are studying this kind of task where they try to look at difference between COT versus non-COT approaches. And the goal of this paper is to kind of abstract out all this like transformer part and try to understand the difference between these two approaches from the setup that I mentioned on the previous slide. And yes, as I said, there are also like these other end-to-end approaches where you just completely like you try to learn this chain of thought by just end-to-end feedbacks. And I'm gonna say once I tell my result, it will be clear like this how these two approaches contrast and what is sort of the right message that one should take behind the success and failures of both of these approaches. So this is going to be my outline. First, I'm going to talk about sample complexity of learning with and without chain of thought. Uh, then I'm talk about some computational separation. And then I'm going to get to this universality and how attention emerges out of this universal learning goal with chain of thought. So let's talk about sample complexity. I'm going to skip a lot of these details, but the point here is just that one table that I want to get to. So, okay, so what if my base class has found bounded cardinality? This is sort of the first question one can ask. Then, of course, if your base class has finite cardinality, then since I'm time invariant, since I'm applying the same function and again, the number of end-to-end mappings that I'm going to get are also going to be bounded by the same cardinality bound. And just by just log cardinality bound argument, you roughly get log cardinality sample complexity for both, whether you observe chain of thought or whether you don't observe chain of thought, because chain of thought observing is strictly as powerful as not observing the chain of thought. But what about VC classes? For example, like this is very, you can say this is a very restricted class. What if just my VC dimension of my base class is bounded? Can I still can I still like learn this class end to end? And the answer is yes. So I skipped the growth function argument, but basically yes, that you can learn this class end to end with sample complexity t times VC dimension of f. So you can think of this as like VC dimension of f is complexity of learning the base class, the base supervised learning problem of like given a sequence, what is the learning problem of learning the next token prediction rule. And then what we are trying to address here is that if I what is the complexity of learning this end-to-end mapping in terms of complexity of learning this base supervised learning problem. So this is the attempt here that I'm trying to capture in this table. And the answer is that yes, in terms of t times VC dimension of f, you can learn this class. But this is sort of disappointing because in some sense, the motivation behind using this time invariant setup was that I kind of, despite the fact that I'm like generating this long chain of thought, I'm looking at this end-to-end mapping after t steps of iterations, I'm somehow learning the same function. And this t dependence is very disappointing because this says that like I have to pay for this amount of time I iterate. Unfortunately, this is also tight in the worst case that you have to like there exists like a time invariant autoregressive base class. This is like sort of uh, worst case result that there exists some base class for which you have to pay this much. And this is disappointing, but this is still about end-to-end learnability where I kind of keep the entire chain of thought hidden from you. What if you observe the chain of thought? In this case, there is like a better learning rule that you can come up with that you just kind of find a predictor which agrees with the entire chain of thought. And since you are in the realizable setting, you will be able to find such a predictor. And we show that with some growth function arguments that with this better rule, the sample complexity is going to be VC dimension f times log t. So what this is saying is this is very powerful. It says that once you have solved this supervised learning based oracle, like basically you have this supervised learning oracle problem where you are learning this supervised learning problem with VC dimension of f. Now, as you iterate more and more number of times, the only thing that you are going to pay is extra log t factor with the generation length. So you are getting this nearly COT independent sample complexity when you have this when you observe the chain of thought in terms of VC dimension. This is what this result captures. Okay, and then it's interesting kind of question that despite that I'm like um, uh, despite the fact that I'm like iterating this like a lot of times, I'm iterating the same function. It feels that even for end-to-end complexity, like you can already see this in cardinality bound that for cardinality classes, I don't pay such a factor of t. So it's interesting to ask like whether you can go beyond VC, whether you can go beyond cardinality and still capture the complexity of end-to-end learning with nearly t-independent sample complexity. And the answer is yes, in terms of Littlestone dimension, you can do this. So it's sort of like a philosophically interesting question, like whether you can shave off this t-dependence in terms of other stronger notions of your base class. And in terms of Littlestone dimension, you can see this. And one intuition here is that the reason why this is possible to do in terms of VC dimension, but not in terms of Littlestone dimension, sorry, I think I said the other way around, is that despite the fact that you are iterating the same function again and again, The process of this auto regression here is sequential in nature, but the notions like VC are fundamentally batch-like. They just, what they count is on a given batch, how many behaviors you can get with like different predictors of your class. So they are like batch notions. And the process of auto regression we have here is sequential, despite the fact that you're iterating the same function. And that's why it is possible to get this independent T complexity, nearly T independent complexity in terms of Littlestone, but not in terms of VC dimension. But this is the table. But the only thing that I want to emphasize here is that all this results in this table where you are not seeing this T like direct linear dependence on T are critically using the fact that you are iterating the same function again and again. And you can directly see this in cardinality class, because if your class has finite cardinality, and if you allow to iterate different function at each time steps, then the number of end-to-end function is going to be the cardinality of f times t, sorry, to the power t. And if you take a look at log of that, you get t times log of cardinality. And even intuitively, like just think of it as if you have t different function to learn at each step, there is no way that you are going to get rid of this t dependence. But if you are learning the same function, then you can ask like whether you can shave off this t dependence. And this is going to be very important for me in this universality result that I'm going to talk about at the end. Okay, and nothing in this table is really tight, at least in an instance specific way. And there are like interesting questions here that you can look at in our paper. And we also have here, I was just looking at like the my token set being binary, just 0 and 1. We have generalization of this result in terms of standard notions for non-binary but finite sigma. And there are like some log factors which are like important to be removed. And there are a lot of technical questions here that are open. Now I want to get to the sample complexity. So all this I was saying was more like a benefit of time invariance than the benefit of chain of thought. In my opinion, the real benefit of chain of thought is computational. And the intuition is as follows, that when you have this internal chain of thought, somehow the global problem of learning this end-to-end mapping has been boiled down to learning these local problems of predicting the next token, which somehow provides you like peek at the internal working of this computation to how to arrive at the final answer. And this extra supervision is very powerful for you to like kind of learn like many hard problems in a computationally tractable sense. And so let's talk about first complexity of COT learning. An attempt here is again going to be to capture the complexity of learning in terms of the property of the base class. So in the realizable case, sort of when your supervised learning is problem is tractably learnable, the gold standard is that when your um, base problem has tractable consistency oracle. And of course, I have to get into this now issues about like input size and hierarchy, like the size parameter of my concept class, which I will not try to formally define here. But the point here is that if your base class has like uh, tractable consistent oracle, then what you can do is you can have your COT data set. You just collect like all your prefix and next token pairs. You break down this COT data set into this kind of pairs, which is exactly how you even train transformers. And then you just call your consistency oracle on this prefix next token pairs. And the computational complexity, assuming that you have tractable base consistency oracle of the base class, the complexity of this algorithm is going to be polynomial in TDN, the input size, the size parameter, and the generation length, all three simultaneously. And so you get like tractable learning. So this end-to-end learning problem with COT reduces to supervised learning problem of your base class. You have polynomial time equivalence between these two problems. But what about end-to-end learning? And for end-to-end learning, what I'm going to argue is that this is not necessarily easy. And I'm going to talk about like arguably the simplest possible base class for which we know that we have this tractable consistent oracle, which is the class of linear threshold. So my class is as follows. I'm going to be on the binary token space, just 0 and 1. And then for each weight in my R to the D, I have linear threshold. I just look at my current input sequence. I look at last d bits of the sequence. I apply my linear threshold and I generate the next bit. And I'm going to do this multiple times to come up with the entire chain of thought. And then the final answer is going to be my end-to-end mapping. So this is my base class, just the class of linear thresholds. And for this, I know that the base class has consistency oracle, because consistency oracle here just is like LP feasibility problem. I just have to find a weight which agrees with all my data, which is just an LP feasibility problem that I'm showing here in the box. And for this even simple class, we are going to argue that the end-to-end learning problem, if you hide the chain of thought, then this is going to be hard. Okay, any questions about this class definition itself? And also like general, like the contrast between COT and end-to-end?
Hi, Nirmit. I have a question.
Yeah,
I had a question regarding the sample complexity. So,
okay,
in the COT setting,
yeah,
you said we would just need VC dimension of the class times log t number of samples.
yes.
But then each sample would have t tokens, right? So essentially, would it be fair comparing the number of samples here, or is it a better idea to compare the number of tokens between the COT setting and the end-to-end setting?
So, okay, good. So this is, okay, so you're saying like, how should I view this result? Like, what is a fair comparison here? Which is a good question. I would say that this is, so, okay, so even if you have like, so first of all, this intermediate tokens are not IID. So it's unclear whether you gain something out of this or not. It's true that there are like this intermediate tokens, like intermediate like prefix next token pairs. But the problem is that all these are highly dependent things, and they each, as you gain all this like extra information, you are not gaining much out of this like they're not independent. Also, the other thing is what I remember that what I care about is my end-to-end agreement error. So in particular, in this particular setup, so this argument here is not the fact that, oh, if I observe this chain of thought, and so it feels kind of a trivial result to say that, oh, if you observe the chain of thought, then you have like a lot of these samples. And uh, what if you kind of just learn like each predictor at each step, then and you have to just learn one predictor, then you're going to agree on end-to-end error. But remember that since you care about end-to-end error being epsilon bounded, in each step you might have to learn each step with epsilon over t accuracy. And even with chain of thought, the naive bound is to, in order to get end-to-end error of epsilon, you have to learn each step with epsilon over t accuracy, and then you directly get t over t VC dimension of f over epsilon with this type of argument. So the fact that here that this somehow end-to-end sample complexity is bounded by VC times log t kind of is doing something better than the argument that I just said. And the fact that you have to agree on this global objective of end-to-end, this is like tricky. But in terms of comparing E2A versus COT, I would only say that this tokens that you have extra are highly dependent, and whether to count them as like t independent things, or you want to count them as uh, this like just one, is like very subjective. And I don't think there is a lot of gain in terms of I don't think these tokens are highly independent enough to give you more information. So just counting them as t tokens will not be uh, also fair, I feel.
Got it. Okay, thanks.
Yeah, great. So any question about this class and uh, this separation result? Great. So I want to talk about this hardness of end-to-end learning. So this is sort of,
Sorry, Nirmit,
yeah.
I don't know if you did it on purpose, but your screen sharing stopped.
Oh, I see. Sorry. Okay, my bad.
No worries.
I think I was just looking at time for a bit. Okay, thanks. Great. So the way this hardness result is shown is that we try to express the class of circuits of constant depth with some time invariant autoregressive threshold. And what we show is that the output of the circuit on all the input will be the same as output of this autoregressive linear threshold once you apply this iteratively. And the construction is as follows: that for any size S and depth, sorry, for any size S and depth L circuit, I can come up with a linear threshold whose dimension is size to the L, and the generation length is S to the L as well, so that up to some fixed polynomial time input feature transformation, I'm gonna realize this output of this circuit as applying the same iterative autoregressive threshold by this construction. And by this, based on the standard hardness result in learning theory that constant depth circuits are hard to learn, I get the interactability of this end-to-end for this basic simple class. So one might say that, okay, this result is nice, but I can also view this result as learnability result because there was something hard that I know that I cannot learn in tractable runtime. But now with chain of thought, with this autoregressive chain of thought for this linear threshold class, I'm going to be able to learn this function class, this very rich function class. And the question is, can we view this as can you view this as learnability result? And the answer is no, actually. So why? The reason is that in terms of learnability result, this result is extremely disappointing because for like, okay, what is the sample complexity of learning this class of size S and depth L circuit? It's just the number of parameters, which is roughly the size of the circuit. But the sample complexity that I need to learn this class is going to be of order D. So D is here was S to the L. So my construction is really extremely bad. What I'm doing is basically for size S circuit, I'm paying this exponential dependence in depth in order to encode because I'm encoding this with linear thresholds. So my sample size here is actually much more than the number of samples that I would need to learn this class directly. So in this sense, this is extremely disappointing result when you view this as learnability result. And the question is, should this motivate us to like try and improve on this result? And I would argue that the answer is no. If like the circuits are completely wrong place to start, given the development that I have been trying to present here. So what is the reason behind this? Because circuits are inherently non-time invariant model of computation. In particular, what I mean by that is that you look at like what is the time it requires for a circuit to arrive at the final answer from its input. It's going to be the number of gates in the circuit, which is the same as number of parameters in the class. So circuits are non-time invariant model of computation. And if my goal were to learn circuit, in fact, then time dependent class is a better suited for this goal. Why? Because each gate is like a linear threshold for me. And if I have different linear threshold that I allow myself to learn at each step, then I can learn this class. So this Malak's construction was basically doing this. And if my goal is to learn circuit, then of course this is the right thing to do. I mean, this is probably a better thing to do. I'm not sure if it's right, because circuits are, and you can encode them as linear threshold circuits. And then this directly implies that there is like a time dependent end-to-end class of linear threshold that can express this class. And of course, like if I just do ERM over the neural network class, then but once I also get output of not just the final neural network output, but also the output of each gate, then kind of this allows me to sort of look at this inner working of this computation. And with this COT, my learning problem becomes easy. I don't have to do this global ERM problem. So if this is what not I care about, then what is it that I care about? And the question is, what is sort of the universality that I care about, and how I should uh, how uh, yeah, so what is the question that I am trying to put here? So let's try to decouple between runtime and the description length of the program. So let me consider this class of programs of just whose description length is at most n. So there are many programs which have like very low description length, but they can learn for a lot of time. And if I want to learn this class, then I can just do ERM over this class of short programs, and I can learn this class in order S samples. But the problem with this class is that this ERM is not only like just not just tractable, it's not even computable, because some programs may not just ever halt, even though they could have very low description length. So this is not even computable. But these programs are anyway useless for you, because if they are not going to be able to hold, then how can you use them at the time of inference? So these programs are anyway like not interesting to you. So what is interesting to you is also like they kind of run in like short runtime. Okay, so let's consider these two parameters, size parameter and time parameter. And let's consider this class of programs of length at most s and runtime at most t. And still the regime that I'm interested in is that description length is much shorter than t. And what would be the dream universality of learning? So what I would like to do is that I want to learn this class. What is the sample complexity of learning this class if you ignore computation completely? By just log cardinality argument, I just need order S sample to learn this class. But of course, if my functions are there, if my functions are running for t time steps, then I must like also like it's fine that my runtime of learning rule is allowed to depend on t, but in terms of sample complexity, I don't want to pay this factor of t. I want to learn this class with either order s or maybe s log t. I'm fine with log factor because it becomes like tricky what you mean by like it like yeah. So I'm fine with log t factors, but in terms of sample complexity, I do not want to pay like this linear in t dependence or polynomial in t dependence. But in runtime, I want to learn this class with like tractable learning rule, and tractability here means that whatever was t parameter, I want to learn in like polynomial in t many steps of computation. This my learning rule should be able to do both of this simultaneously. And this is sort of my dream universality learning goal. So what would be, so the question that we try to ask is there sort of natural iterative base class, my universal base class f, so that it has enough to express such universal class of program s comma t. I can express this class of this universal class as the end-to-end mapping of this my iterative base class. And then this base class is learnable with like very low sample complexity and s log t. And now you can already see that why this getting t independent sample complexity result was very important is because if I want to simulate order like t steps of computation, then my chain of thought are going to be of length t. But I don't want to pay in terms of sample in order to learn this if I have sort of time invariant structure of the class. So my sample complexity has to be like nearly independent, like either independent or nearly independent of t. But then what I ask is like it has to be also be tractably learnable with COT. And this is sort of my universal class. If I can do all these three simultaneously, then I get this universal dream goal. And let's try to intuitively think like what kind of implicit requirement this puts on a structure of the base class that one should have. So I argue that we should have somehow high context, low complexity base classes. What I mean by that is that, again, if I want to simulate a runtime T computation, then I must have to attend to tokens which are T far from me, like T far in the past, because I'm going to encode my computation as chain of thought. And I want to attend to tokens which are T far from me. And in order for samples, like since I'm asking that my sample complexity should not depend on T, I want these classes which have very high context, but low sample complexity. And the reason why you can already see that why linear threshold will not be able to give you this universality, because what happens is that in order to attend to tokens which are d far, you have to have a linear threshold of size d. And once you have a linear threshold of size d, then in terms of sample, you have to like kind of pay for this cost. Okay, I mean, this is still an upper bound, but I think it's very hard to say that you don't have to pay for at least like one step of learning. So this is here. This is the reason why linear classes are limited. And then one thing is like, what about like sparse linear predictors, where I kind of like what is the complexity of learning, which is like sparsity parameter. And the context could still be very large, but I have like sparse. And this is like very interesting question. It already satisfies two of the three desiderata that I mentioned above, but unclear like whether they are expressive enough to encode this universal class that I mentioned that I want to express. And it's interesting when most likely I suspect the answer is no, that sparse linear thresholds are limited also, but I don't know how to show it. And the question is then what is the base class that would achieve this universality? So roughly speaking, the idea is that is to use attention. So what I'm going to do is I'm just going to tell you intuition, because the exact notation is not very important. And probably like a lot of these ideas have appeared in many of the papers. I'll just try to tell you the intuition and like what is the new thing other than previous results here that I like about this result. So what you do is like you encode the entire history of Turing machine computation, which is like the sequence of state, the symbol it read, and the move, and you encode them as like your chain of thought. And then at any point in time, and your base class is going to be the sequence of all, like it's the class of all transition table, the autoregressive next token predictor rule that you have for each transition table. And what does this rule has to do based on the history of the computation so far? What it has to do is to calculate the current position of the head, because the Turing machine has taken like a lot of moves so far. It has to calculate the current position of the head, which is just like summing the positions, like summing the moves so far to arrive at the token, to arrive at the current position. And then what it has to do is it has to match the current position with the previous time the head was at the same location. Okay, so this is sort of like finding the most recent token in your history so that the position agrees with it. And then you have to retrieve that symbol, whatever symbol that was written at that location. And once you can do this, you can take the next move and you can arrive at the next token. So these are the sort of things. And by definition of this class, of course, this the universal class is expressed by this end-to-end mapping of this class. And it's very easy to see that this class is learnable with s log s samples, because my number of transition tables that I have, the log cardinality of this class is just s log s, because I have h to the s transition table roughly, and log cardinality is just s log s. And I can also learn this class in polynomial in t runtime, because remember that this base, all I have to do is I just have to find a transition table which is agreeing with the entire chain of thought. So this I just have to go over all tokens and I just have to find a consistent transition table. And my base class here has consistency, tractable consistency oracle. So I get this all three decider rata simultaneously, and I can enjoy this universality. So roughly speaking, what I'm telling you is that if you break your problem enough, I can provide you this extremely rich supervision of this the state action transition table that your tuning machine took. Then essentially you can learn this, like achieve this dream universality goal. This is what this result captures. And sort of when you observe the form of this base class, then there are like two operations here. So one is this summing over all tokens so far, which is like a uniform attention. You have to kind of find like uniform mass over all these tokens, and then you have to look at the sum of the moves that you took so far. And the second operation is that once you find this current, like at any point where was this head, then you have to sort of look at this matching operation, where like what was the previous time in the history when my head was at the same location. And this you can also express this as some kind of attention. I'm using here average hard attention, this AHA, which is just like uh, zero temperature limit of my standard attention, which you might be familiar with. And using this average hard attention, you can express both of these operations. So what we try to argue here basically is that when you ask this universality question and ask like, okay, what is sort of the natural autoregressive base class that would achieve this universality, then the definition of attention, at least this average hard attention, is staring within the form of this autoregressive base class. And once you can think that from here, okay, and I really get this structure of like I have this two-step of attention, and in between I have some local operation, and I kind of gives rise to this transformer type architecture where you have a lot of attention heads interleaved with like local like ReLU MLPs, local multi-layer perceptron, which are just there for computing these local steps. And and then like when you want to exactly give like formal result in terms of like softmax and a real transformer architecture, all these issues like how much precision you should need, then this becomes very important. And then like this, whether like you have to encode what is the position encoding that you would use in order to use, and these issues are also very important. And somehow all this work that I'm mentioning here address this issue in a very good way. But the point of view here we take is sort of reverse. Like we ask like, okay, what is the if what is the class that would achieve this decider errata first? And then we ask like, okay, what is the natural base class that would achieve this? And the definition of attention is within the this description of this base class. This is what I find interesting about this result. So any question about this universality result? Okay, great. So this this is mostly like a change of perspective, this result. And just the expressivity is not enough, because I know for a fact that just expressing doesn't tell me. And then this proof looks very rosy, like it seems like everything is trivial. But there is like one non-trivial thing that happens here, is that like, okay, I would only say that it's not possible to get this universality in the agnostic setup. And there is the fact that you are realizable makes like some things very easy for us. And the fact that there is this autoregressive base class which also gives you like computationally tractable learning, this fact is non-trivial about this result, because you can get expressivity, you can get sample complexity, but the fact that there exists such a class which also has this tractability property is very non-trivial about this construction, and you will lose such a property when you have agnostic setup. So, okay, let me just summarize by what we have done so far and try to conclude with open questions. Let me see the time. Okay, I have like 5 minutes. Good. Okay, so as I said, this COT supervision is really something that happens in practice. Companies are investing efforts and money in like collecting these type of data sets, either by human labelers or like using strong models to even generate this rich chain of thought. And on the other hand, there are this end-to-end approaches which also have like recently gained interest, like just training based on this end-to-end feedback. And what this result shows is that it's not possible to for these approaches to succeed without making any assumptions about like at least in the setup that we mentioned, it's not possible for these approaches to succeed. And what are these assumptions that allows this tractable like this approaches to succeed is like very interesting question. So one most plausible hypothesis is that this 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 rule somehow have like this coverage property that after this pre-training or this supervised fine-tuning phase that happens, they have enough coverage over the set of good responses so that then this RL approaches, this end-to-end feedback can kind of elicit this behavior that are already there in the base model. And this is sort of one, and then you can enhance this behavior with only end-to-end reward. And it's very interesting to understand like what is this coverage property and how it is achieved even during this like pre-training phase that that then is elicited during the reinforcement learning step. What we are presenting here is very interesting framework to contrast between these two approaches and try to see what is this like intermediate regime that people are currently working in. One reason that you want to go away from this COT supervision is that the COT supervision you can think of is a very expensive. Like it's very hard to come up with this type of risk supervision. I showed you like these two regimes where one regime is most of the thing is hard because it's just classical pack learning of end-to-end class where I hide the chain of thought and I give you like detailed enough chain of thought and then I showed you like essentially everything is easy to learn. And most of the time the situation is not as black and white. It's kind of gray. And the COT supervision is like we kind of have enough COT supervision that we know that these problems remain like somehow are easy and we are succeeding in learning. But sort of what is this minimal number of sample that one needs? So with this time invariance and stuff, we brought the sample complexity requirement down. But still, there is no inherent lower bound here. So why this COT learning is possible even? Is this possible to do with really few short COT examples? I don't know the answer. It might be that just like one example is maybe enough to break the hardness barrier of end-to-end learning. And this even for like the simple class of linear threshold where I showed that end-to-end learning is hard. I don't know whether just one example is easy, whether just like few examples are easy, and how few is this few. I don't know answer to these questions. And it's very interesting to show either hardness results or like show like yes algorithmic possibilities that oh very few with very few COT examples and then lot of these end-to-end examples that yes you can think you have abundant where you can somehow create this like good algorithms to learn end-to-end mappings. This is like very interesting direction. And as I said, like in real things, the situations are much more grayer than even this. So what we have is that, so I was recently reading this like Apple people, Amani et al. From folks from Apple, who would really do something interesting. So what happens, they observe that this supervised fine tuning is, of course, it succeeds. And this RL also struggles, but coming up with SFT data, as I said, is expensive. But just doing RL also succeeds. So what they try to do is they have the supervised fine tuning data. They reveal like small parts of it, and then they allow them to complete the rest of the chain of thought. And what they argue is that this approach somehow kind of is better than both these different regimes of just SFT or just RL. So in terms of this class of linear threshold, you can think of this as you have kind of this internal chain of thought of linear threshold. And what if I reveal like some prefixes of them, but I let you complete the rest of the prefixes? Somehow, what is this, gray regime in between in which you can still succeed? There is still like algorithmic shortcut that has been created, which I know for a fact that end-to-end learning is hard. If I reveal you enough the entire COT example, then that's easy because I just showed you both of these two regimes. And it's interesting, like what are these intermediate regimes in between in which still you have this end-to-end tractable learnability, and this is very interesting direction. And uh, one particular setup that I also find interesting is like what if you have supervision from like multiple experts who have different chain of thoughts, but they have the same final end-to-end mapping. And sort of how much this can hurt or help you, I'm not sure. And this agnostic setting, this is really getting to the agnostic setting, then what is even the right model of misspecification? So what I don't understand for this agnostic setup is that what are the real ways in real world in which the COT data can be misspecified, so that then it is interesting to study them. And this particular setup that I said, where I have the supervision from multiple experts, I consider it as one important kind of misspecification, because even though each of my example will be realized by a single function in my class, this entire data set that I may get out of this rule may not be consistent with any of the hypotheses in my hypothesis class. So this is kind of one important type of misspecification that I considered. And there has been some study by Rohatgi et al., people from MSR, about this agnostic setup, where they already see that there are like interesting trade-offs that appear, and even the universality result that I said, as I said, like there is something, it feels like a rosy, like everything is smooth and there's nothing non-trivial. But once you go to agnostic setup, this fact that you can enjoy the same sample complexity as end-to-end learning suddenly breaks down, because your COT problem and end-to-end problem have like very different like global, and there is like computational statistical trade-off that appears in the agnostic setup. Uh, and of course, like there are two parts, as I said here. One is like COT part, and one is like autoregressive part. So COT is something that is happens really. And these days people are also moving away from autoregressive models. And one can also like look at function classes which are non-autoregressive in nature, but still keeping the COT versus non-COT aspects of the problem as it is. And you can model this situation in Paxtel framework and try to get this type of contrasting results. And of course, like one is to be careful about how they define this, but these are sort of broad future directions that I think would be interesting. So that's all, and I'm happy to take any questions if you have.